So video for speaking, my first time video back. I'm really happy to also give this talk because, well, it's classical than the other talk, and it's fitting because I'm Italian, and usually I'm not that kind of Italian to be German. But it's really everything started from the Japanese. You will see a lot of you will see like we start from the first thing I was going to speak about the Ithaca philosophy. I should tell you that this is finished joint work with Mendes Lopez Pardini and Cugino Mendes Lopez Pardini. And then I will try also to, for the varieties, not the surface, I will try to tell you about some work in progress with Baudin. Okay, so what is Ithaca philosophy? So that we have, it's a tale of two works. Then actually one contains the other. On one side, we have the projective work, which we have X. Everything is going to be overseen. X was projective. Then we have the sheet of regular form. So we take the dimension. We take the top external power of this, and is our canonical framework. And then we can use these to produce invariant for x. So we have, for example, that the irregularity of x is the dimension of the homology of the zero homology of big omega x. And then we have Pm of x, which is the dimension of x omega x tensor m. And this is an m origin of we have also the Kodaira dimension, but well, I will put it in another board when. So then introduce the other board, which is a quasi-projective board. Which we have B, which is smooth quasi-projective. And so we know that the Hieronymic theorem of the singularity, we really can consider V as a pair with D with X smooth projective and D simple number crossing divisor. Now we can consider on X, we can consider the shifts of logarithmic form. These are meromorphic form on X or a rational form on X that have pole just along D, and these polar logarithmic. And if V is smooth, this is a vector bundle of the same dimension, let's say also the same dimension of V, V. And then so we can take the top exterior power this, and this is going to be a line bundle, which is exactly yes, which is exactly omega x twisted by the divisor D. And see, this is called the log canonical sheet. Sheets, we have homology, we can use this sheet and homology to produce invariant. And so, for example, we have the logarithmic irregularity of V is the dimension of the zero homology of the sheet of logarithmic form. And we have the logarithmic Furigenera of V, which are the zero homology of X over V tensor. And it's a bar. And it's like made a choice here of smooth compactification, and these sheets depend on the choice. The invariant do not depend on the choice. You can show that these do not depend from the choice. Like if I take, if I blow up X in a point or something, then I will get I might get it. Of course, I get a different space, so different sheets, but the invariant are going to be another invariant is I will take a mention. We continue here. So we, on the projective side, we have the codiary dimension of X, which basically what happens is you take the linear system defined by omega xm, and well, if this is always empty for m bigger than 0, then you say that the codiary dimension is minus infinity. Otherwise, you have a map reduced from X some Pn, and the magic of it is the dimension of the image stabilized when M is big and divisible enough. And this is a codiary dimension. Yes, because like if you consider, for example, a bielliptic surface, so it's the codiary dimension is 0, but so you might have some cyclic pattern. So you want that M is divisible enough because like M prime does not work. It might not give you the right dimension, but M big enough and with many divisors, then will give you what you know. And then on this picture actually works if we put here any line bound. And instead of the codiary dimension, it's called the Ithaca dimension of that line bound. And so we have the logarithmic codiary dimension V is the Ithaca dimension of the non-canonical line bound. And so we have logarithmic invariant. And the Ithaca philosophy, let's start it here, so it's so that to any statement in projective one governed by the behavior of force should correspond to the statement in force projective one governed by the behavior. We should not be bad. I think it's if there is some kind of you can in the projective world you can characterize this property by the behavior of just using the ion produced by force. There should be that we should be characterized also in the quasi-projective world by using the logarithm. And today we want to find a quasi-projective analogous this theorem and request in 1905 Chen Hakun in 2001. They say that if S is a smooth complex surface with U of S equal 2, and P1 of S equal P2 of S equal 1, then S is bidirectional equivalent to what is your variety? So the original one, I guess, was with P1 and P4, but then Chen and Heiko managed to reduce to P2, and actually Chen and Heiko result works in any direction, not just was. And okay, so
for Enrique, it was P1 or just
if P1, if P4 is 1 is 1, the other in the middle. So because you have so it's so you have that omega x is effective, and so it's so you have inclusion. So okay, so this is what we want to do. So the first thing is, what is the abelian surface in the quasi-projective world? And then these I will swipe under the carpet, because it will take an entire seminar to explain precise the notion of equivalence as we need. But one thing is that these invariants are preserved by Barashin and the group. These are not. Because if you just take Pn and you remove an hyperplane section, what you get is a quasi-projective variety that is birational and equivalent to Pn, obviously, but the invariants are completely off. Now, you know that these are preserved by proper birational map. Yeah. So the thing is, so by this is not, so one would say that, right, well, maybe the right notion of equivalence is proper birational equivalence, but it's not okay, because then you will have that if you take an abelian variety mentioned 2 and above, and you remove a bunch of points, that is, the inclusion map is not proper birational, not proper. And so it's this is too, the equivalence classes here are too small. Then what Ithaca did was, well, introduce this weakly proper birational map, in which basically they are generated by proper birational equivalence and immersion with the complementary as codimension at least 2. But this was still too small. And then he did a saturation and he arrived to this. So the right notion that we're going to have here is those of WWPD equivalent. Which seems a high notion of birational equivalence for open one. And so it's weakly weak by rational equivalence. And there is also our W infinity equivalence, but this is enough. Okay, so to 1 billion in this setting. So let's bring the table. So we have objective words. Then we have a positive objective word on the other side. And here we have a billion surface. So they are quotient of CG by lambda. Lambda is a maximum finitely generated region. And we know that the shift of regular form from medium variety is trivial. And so the canonical bundle, the medium variety is trivial. So we have that the codonic dimension of A is 0. Irregularity of A, so it's trivial of dimension of rank G. So the irregularity of A is G, equal its dimension. And all the plurigenera of A are 1. And now let's say what we have. So on this side, we have semi-abelian variety or quasi-abelian variety, like depending what terminology you prefer. So they are algebraic true. That sit inside G. A sequence like that, where this is a abelian variety. And there are standard compactification, like there are 2 of them. We're going to use both of them. So there is a standard compactification in which Z is here. Another compactification that we are going to use is that Z yes, G is open in that. So what happened is that you construct a PR bundle that has these as a associated to this, like you compactify, and you want that the GRM embed equivalently in the fiber, then you construct a PR bundle. The no G delta is simple normal crossing. There is also another quantification in which basically you have the fiber product of RP1 bundle over fiber over K. So this is another way. Once you have this, you can compute the logarithmic invariant, and guess what? You have that the logarithmic codaric dimension is 0. Well, you really have that the omega d log d is trivial. of same dimension. And so you have that omega dB is trivial. And so from here you get that the log irregularity of G is equal to the dimension. And all the plurigenera are 1. And since all the plurigenera are 1, well,
Omega. Omega. Seems to be trivial, right?
it's like the canon, the shift. Yeah. Say that. So this I'm not sure. So this is it, but then the analogy does not stop here. Can you see? So on the projective side, we have the construction. We have the construction of the Albanese variety. So if we have X smooth projective, exists, okay, with X, X, with, so X is an abelian variety, and it satisfies the obvious support. We map to an abelian variety factor in a unique way to the Albanese. This map is created by integrating one form over one cycle. And then you can B move. We have RB, RB. So this is a semi-abelian. Satisfy the obvious universal property. And the theorem of Enriquez that we have here on Chen and Haeckel, like the way which is proved is that you show that the cohomological invariant make it so that this map is Lagrangian. And so you see that it's entirely governed by form because there are invariants produced by form. And then there is a map that is produced by using forms that give you birational equivalence. So it's exactly, if you ever seen the construction of the Albanese variety, so you thing is, so there are two ways to do it. One is with hand, and the other is that the logarithmic form are closed. And then you just do what so this work, the logarithmic form are closed will work also in any characteristic. But then in the projective case, what you do is you have x0 of x, omega x. You choose omega 1, omega q basis, you say here. And then you have H1 X E. And here you have gamma 1, gamma 2Q. And then what you do, you have AI, what is it? They have to be in yes. So AI is omega 1 gamma I. Gamma I. So these are independent. And so they form, so these are independent and they form lattice in C. And so what you do, you consider lambda to be generated by the AI, and you have the Albanese of is okay, so let's do the right modification for the. So now you have and you think so this is going to be bigger for E, like so what you take a basis in which the first Q are a basis of omega x. Then you have in which these are actually logarithmic. Okay, now you look at this, and this is you also here you have more space, and so the thing is, but you don't have twice. You don't get to 2R. You get exactly. Change letter. When you mod out is not maximal rank. Yeah. So, when you mod out is not maximal rank, and actually you in over C, you know that G semi-abelian. So G is always some CG over the fundamental group of G, and this is a finitely generated abelian group of rank bigger or equal the dimension of yes. So it has to be bigger or equal to the dimension, and then of course bounded by 2 times the dimension because it cannot yeah. Three bigger group. Yes. And then when you have equal to G, you have to the abelian variety. And when you're equal dimension of G, you have more abelian variety. There is just G alone. And it's exactly the same proof, and then you construct this, and of course, and then you get a map by integrating. So if you have x, you integrate you choose a base point in x, and you integrate from x0 to x, and it gives you a map to this. It's exactly the same construction. So okay, so let's start standardizing. before I even were born, there was this theorem of Ithaca from 1979. They say that is B smooth quadratic things with um you have you two the and the bar of B equals 0, then of B from B to Z is birational. And there is B0 inside B and finitely many points. One PM in B such that of B restricted to 0, 0 of B minus 1 PM is proper value. And this one,
sorry, zero is off.
says, so this is exactly so now you have result involving asymptotic invariant, arithmetical error dimension, means natural to one. Well, can just choose, can I say that I know that this is true if I fix some to the general to be what? Sufficiently I to the general to be one. And this is what we did. I came from this and I come with the Rikeston and Heikon as a projective side. First, here since my result of today is this is this focus here. Since that if B smooth reduction, other reduction, this with 5 of B of 2 and B is WWPB equivalent to an Abelian surface even only if so either one the irregular equation bigger than 0 p bar equals 2 4 The irregularity x is 0. 1 of b equals 3 of g. So these two are equivalent. And you see why I find that the result does not. So in the data result, the statement that you get does not need to be verbatim what you go. You don't have to expect that it's going to be verbatim what you have in the projective. So you have something different here. And this statement is short. So nothing better can be done here. And I will show you an example.
Why is that it will also fun?
Before, because it means that so P1 means that omega xt is effective, and it has just one section. So omega twice the power is in between the two, and it has at most one section, but it has more than one section. So it's one section. Okay, so this is sharp.
In the statement, what is x?
So
Part 2 tables. They confining.
So yes, so it's so if it's not affine, then it's well,
If it is applied.
if it is affine, then you are here, and you need 3. Yeah, well, if it is you need 3 because if it is affine, then the compactification is P2. So the regularity of P2 is 0, and so you will need. But if it is affine, yes. But still irrational. Sure, because also.
Right.
Well, it's
and remove the
really sure. If these are fine, the compactification of 0. These I'm sure. Okay, B is going to be 2. Also because if you go back, if it is a fine, then it's isomorph. It will be WWPB to GM. And then the compactification is the. But it is a fine, the regularity is 0. The regularity of the compactification is. Yes, this is. It doesn't mean that I'm saying it. Like it was already in the work of Ithaca, because a corollary of this, since WWPB is really strong, so you know that if B is so WWPB equivalence between affine varieties is an isomorphism. And so a corollary of this result in the same paper is that if B is affine with the same invariant, then B is GM2. And so as you can see also corollary of this result that if the B is affine and the first 3 plurigenera are 1, then V is GM2. It's because it's WW equivalent to GM2, but the WW equivalent between affine varieties is These are the grounds. So, but yeah, so there is this example that I have to choose which one I want. Yes. So let's do this one. So if you I take E an elliptic we say J invariant 0, like with the O in out in with the automorphism of order 3. So I would say J invariant is 0, not 1. So now what I do, I consider E cross E quotient by the diagonal involution induced by rho and rho squared. So this is singular. So order 3. Oh, it's a singular. Okay, sorry. So this is singular, but I can take a resolution of singularity, and this is going to be a K3. So it's singular because there are the ramifications. This is a K3 surface. And it's a particular K3 surface because it has 3 fibers. These are elliptic K3 surface. And there are 3 fibers. 5. 4 star. That if you don't have the data classification by heart, so these are the ones that and let's have to put the number correctly. Yes, it's 3 to 1.
0.1.
Fine. They are. You have 3 of P1, multiplicity 3, 3 with multiplicity 2, and 3 with multiplicity 1. So what you do, you take you have
Sorry.
It's a what are the 5?
1 fiber.
3.
3 fibers, all of them of this form.
Yes. It has 3 fibers of this form.
I go first.
Yes. And so you have Fi and this fiber. You consider Fi reduced. And then you take X minus 1. So you take X and you remove these 3 fibers. Now, you can see that these 3 fibers do not move. Twice these 3 fibers do not move. But three times these 3 fibers, it moves. Because if you take 3 times 1 of these fibers, it will contain a whole fiber. So you have that 3 is contained in the fiber. Because like 3 times, then you have and so you see that the third plurigenera is not 1. So Yeah. So this is V. So the Pi of V is, you can have P1 of V is equal P2 of V equal 1, but P3 of V is equal 2. And the Albanese map of this is not dominant. Yes. V is K2 minus the 3. So what's happening here? And why the Albanese map is not dominant? Let's make a picture. So you have an electric vibration. You have these 3 fibers. So you have that basically V maps to curve of logarithmic genus 2. You have that the irregularity of V you can show is 2 because there are no other algebraic relation between the elements. But you have V map to this open curve C, and well, you have that V is really factor of the Albanese, and this is going to be isomorphic to the factor C. So the image of the Albanese is and so it's not dominant, and so this map cannot be WWPT. So the result is actually sharp. There is nothing that one can do. So the question is, what about higher dimension? And in higher dimension, there was a theorem of Kawamata. Is one. Basically, this tells you that if being smooth, quasi projective with angle of V equal the dimension of V, and the logarithmic order dimension of V 0, then V is birational equivalent to a semi-abelian. And together with Fujino, Mendes Lopez, and Pardini, we were able to strengthen this. So instead of Schimmel equivalence, we really have WWPD. So there is a hope that our results can be extended in any dimension. And I used to have 2 conjectures, one bold and one okay, but now that I've worked on this a little bit, my conjecture is
For seven.
yeah, any dimension, everything in the
My question was this WW diamond.
it's the same. It's there is who 0 inside B open and C inside B with codimension C greater or equal than 2, so that the Albanese of V restricted to V0 from here V0 to alpha. V minus C is proper variation. So the thing is, you have an abelian variety, you remove something of codimension at least 2, so what you have is going to be double. Also, you can plot, you blow up something of dimension 2, then you remove the effective divisor. Let's see inside the LV. Well, so I give you the example now. Suppose that LV is actually an abelian variety that could happen. Then the typical is that you blow up something of the dimension at least 2, and then you remove the effective divisor. Then it's so, and then this would be. The conjecture I have is that there should be a bound the M0 depending only from the difference between the log irregularity of V and the irregularity of a compactification of V. Such that mention what the one dies is to here. Yes. So it should be M0, well, in the M0. So it's the MZ that depends just by the depends from the difference. So it doesn't depend the dimension, but it depends on the difference. M0, like MZ, so it's bound. It's a M0 that depends just. It doesn't. So it's in M0 that depends just on the difference between the log irregularity and the irregularity of the compactification. So that if V is the dimension of V and these are all one, it means that is the equivalent to, let's say, a million. I would say yes, but in some sense it depends, because if the dimension low, this can be arbitrarily big. Because for surface, if Qx could be 0, 1, or 2. So the delta here could be 0, 1, or 2. But of course, for a threefold, then the compactification, so this is 3, and the compactification is, compactification can have 0, 1, or 3. So this delta can be 0, 1, 2, or 3. So it's so as the dimension grows, there are more things, but I will guess that it doesn't depend on the dimension, and we have some hints. So it's now with the working process with Bodin. So We can do the baby case in which this is 0 in any dimension and 2 is enough. And we think that 2 should be also enough when this delta is 1. And we have made some progress. So I have like 3 minutes, and well, I want to give you into the strategy of the proof. So there are basically 3 steps. So there are 3 steps. That is, the first one is alt V is dominant. And the second one is alt V is birational. The third is an alt V is WWDD. And we really did the 3 cases. So these 2 were a piece of cake. There's some work to be done, but the reason why they were a piece of cake is because we could use the powerful theory of generic vanishing that was a key for that the key for Chen and Keiko result about the video. And then here there was some work to be done. And these still using generic vanishing were quite easy. This you don't want to know. It was a nightmare. We got stuck here for like 3 years. So it's then once this was done, this part was okay, but then this was again difficult. And in sense, that's one of the reasons for which I really like this project in general is that, well, first it's used technique that was just for projective geometry, but we managed to apply there here. And then you can really see the 2 sides of the difficulties of the geometry of surface. So at the beginning, people were like in the very old day, people were just studying regular surfaces because they thought they were easy because having element in the peak knot make it more difficult. But then they realized that they could use Albanese to say something on the geometry. But still, so you see, they thought they were difficult, and there are something that are more difficult on irregular surface, and there are something that are way more difficult in regular surface. So you see all the chromatic shade. And for that time, I don't think so, so I will stop here. And, yeah.
Any questions or comments? Yeah, I have a question. So you give example where this example is for tricks. So you want one of example?
No, there is another one. So you can take you take P2 plus P2, and you take a ramified coin on 3 fiber, like you have a 2 plus P2, and you take a ramified cover, ramified in this configuration. This is singular in this 9 point. Up you singularize, and you get again K3 surface with
what dimension? say maybe
you after you get again a K3 surface with this configuration. And I think this might be so then it's the RK3 surface with this configuration, the only counterexample I would say yes, because the way in which so the thing is, we run the proof, and then there was at a certain point in which we were comparing, we knew the Euler number of X, and then the only possibility, so it's, then so we had a Q equal 0. We had found that there were only two cases. There were P2, or for the compactification was either P2 or a K3. And then we say, if it is P2, blah, 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 and it worked. But if it were a K3, then we were comparing the Euler number, and we said that with the Euler number, there was exactly this possibility of a K3 with this 3 fiber here. And then we sat down and say and so that this was not working actually. And then it's I think it was so this was Margarita, but I think it was well known that you can get a K3 with 3 fibers of type 4C. Create a modular space. It might be. I think it might be. I don't know how many cases. Like I don't know if it's humanly possible. It's yeah. So we are trying to do some, not on this. Is we're in general type, and we are trying now to see if we can do something like there are characterization of product of curve of genus 2. We want to see if this transpose into the logarithm exactly, but I will not know if, like I've never thought of it. I don't know how many cases it could be.
Yeah, they're pretty eloquent. The next was also for the later